reviewing how to do the basic ionic compounds. So remember, in this, with each one, you always take, if it's from the name, figuring out the formula, like these first four, you're going to list the symbols, assign the charge. Metals will always be a positive by their group number. Non-metals will always be 8 minus their group number, and that's a negative charge. So sodium, looking at the periodic table, it's in group 1A. Look at the top of the column. Remember that it's the number in front of the capital A. Nitrogen, though, is over in group 5, so 8 minus 5 tells you that it's a negative 3. Once you do that, then the next thing to do is you're going to swap the charges to figure out the formula. So what I mean by this is the charge on the sodium actually tells you how many nitrogen. The charge on the nitrogen tells you how many sodium. So you just take and swap. Don't swap the plus and minus. Just swap the numbers from the charge, and that'll tell you the formula. So this one then comes out being Na3N. So then the Ca with P, calcium phosphide. Calcium's a +2, it's in group 2. Phosphorus is in group 5, so 8 minus 5 tells you it's a negative 3. So swapping these, the metal is always written first. There's going to be, bless me, there is going to be 3 calciums because that is the charge on the phosphorus. And there's going to be 2 phosphorus because that's the charge on the calcium. Okay, so we did these ones. So looking down on the next group of them, when you have a formula, it's pretty nice. If you have the formula for an ionic compound, you always just use the whole name of the metal, first part of the nonmetal, plus IDE, right? So K2S, K is potassium. So K becomes potassium. And the S, which is sulfur, so you take the first part of the nonmetal and then add the IDA. So that becomes sulfide. So it doesn't matter how many of each there is. This is the only way that they can react to form a neutral compound as an ionic compound. So lithium combines its Li3P. So lithium, whole name of the metal, lithium. First part of the nonmetal, so phosphorus is phosp, and then you add IDE. Okay, so looking at those nonmetals, so carbon would become carbide, nitrogen, nitride, oxygen is oxide, fluorine is fluoride. So you always just taking the very first part of that nonmetal plus the IDE. So where we stopped last time, we were going into the 2 kind of oddball groups, and those are, the first one I started talking about what are called transition metals. So transition metals are the ones that you find here. So transition metals, if you look on your periodic table, notice that you have a capital B at the top of their group number, not a capital A. That capital B tells you, 1, they're pretty big, and 2, their energy levels have a lot more orbitals to them. So remember the first energy level where hydrogen and helium exist. There's only just 2 electrons in that first energy level. That's all that fits. When you go to the second energy level, remember I told you that there was 8 was the maximum. So the second energy level, you can have 8 in that one. The third energy level, we can hold 18. And in fact, going across from sodium, magnesium, all the way across over to chlorine and argon, those ones really straightforward. When we get to that 4th row down, that's where those transition metals can be found. And these actually end up having kind of like an extra orbital possibility. And so they can lose different numbers of electrons and become stable. So the only 3 you have to worry about are 3 that we will talk about again over the course of the semester. Chromium, which is Cr, iron, which is Fe, and copper, which is Cu. So those 3 that I have boxed, you see that they actually can exist as 2 different possible charges. you can't tell from looking at the top of the group. So looking at the top of chromium 6b, that doesn't tell you anything about the charge. So you can't figure it out. Unlike the main group, the first 2 columns and the last 6 columns, if you look at the group, you can figure out how many valence electrons they have. But you can't tell that from looking at the transition metals. So these ones you have to just remember. So the only 3, chromium, iron, and copper. Oh, let me go back one then. It's here. Okay, so since iron, chromium, and copper with these, iron can be a +2 or a +3. So what this means is you can end up with compounds of iron combining with the same nonmetal, but you can end up with different combinations. So I can end up with FeCl2 or FeCl3. Chromium, same thing. Chromium can be a +2 or a +3, so you can end up with CrBr2 or CrBr3. Copper can either be a +1 or a +2. So in this one, you can end up with like Cu2O or CuO. So the big question is like, well, how do you tell? Okay, and how do you indicate what the correct formula would be? Because that means there's always going to be 2 possible formulas that you can end up with. So that is where this comes into play. So the Roman numeral indicates the charge on the metal. That's the big thing to remember. The Roman numeral, this tells you the charge. It doesn't tell you how many. I will tell you that is like the biggest mistake, is that I see students like saying, well, if it's iron 2, that means there's 2 iron. No. If there's iron 2, it means it's a +2. But once you know that, you really just solve this exactly the same as you do the other examples that we've been doing. So for FeCl2, you need to figure out what the charge on the iron is if it's not given by the name. So if I see FeCl2, I'm really like working backwards to figure out the charge. You know the charge on the chlorine. What will the charge on chlorine always be? The -1, right? So do you see in this formula that FeCl2 is 1 iron? Do you see that the -1 and the 1 for the iron are the same? So what is that going to tell you about the charge on the iron compared to the number of chlorines? It's going to be like a reverse swap, right? So remember, you assign charges and you swap. Well, in the same way, as long as the nonmetal and the metal numbers balance, like they're the same, then you can do like this reverse swap. So this 2 tells you it's a +2. Okay, so we did this when given the name, you figure out the formula by assigning charges. Well, in this one, I'm giving out the formula, and since it's one of these 3, if I just do the reverse swap, I can figure out what the charge on the iron is. So then I know what is this one's name. If it's FeCl2, it's still going to have, what's the name? Iron chloride, right? But because the iron is a +2, you're going to put a Roman numeral 2 in between. You can use parentheses or not, like your book is really good about using the parentheses. It doesn't really bother me if you forget the parentheses. I would not mark that wrong. But see that it's the 2, +2 is the reason why it's a iron 2 chloride in the name. So then if you look at FeCl3, same thing. Iron, or the chlorine, is still a negative charge. So notice that the number of iron and the charge on the chlorine, same. They're both 1. So that means that the charge on the iron is going to be, so this is a -1 and that's a 1. They're the same. So that means that the other ones are the same. So the charge on that would be a +3. So you're sort of working backwards. So the formula can help you figure out what the metal charge is. So then when I write this one's name, it's still iron chloride, right? That's no different than how any ionic compounds are written. Whole name of the metal, first part of the nonmetal plus IDE. But if you have iron, copper, or chromium, you've got to put the Roman numeral. So this one would be a Roman numeral 3. Telling you the charge on the iron. Okay, so let's do some of these ones. So going down, here's 4 right here. So we have copper 2 chloride, iron 2 nitride, chromium, whatever, iron, whatever. So from the name, tell me the formula. From the formula, tell me the name. And if you didn't get one, so going from the name to the formula, I think it's a little bit easier because you know how to assign that charge automatically. So if I see copper 2 chloride, what are you going to put? Cu and Cl, right? And then what's going to be the charge on the copper? Nope. +2, right? So the Roman numeral tells me that this is a +2, right? That makes sense? Okay, so if you're given the name, the Roman numeral tells you the charge on that weird metal, the metal that could be one or the other. But you know the charge on the chlorine is going to be negative because it's in group 7, right? So remember, 8 minus the group number tells you the negative for the non-metal. So now I just do the same thing. Swapping them tells me the formula is what? CuCl2. The charge on the copper tells me how many chlorines. The charge on the chlorine tells me how many coppers. So just swapping those charges, that's already simplified. It can't be simplified any further. So what about iron 2 nitride? What's the symbol? Fe and N. Okay, so then assign the charges. What's the charge on the iron? It's a +2. The Roman numeral tells me the charge. The charge on the nitrogen is -3. So 8 minus group 5. If you look at nitrogen, it's in group 5A. So 8 minus 5 tells you it's a -3. So now if I swap these, the formula N2. Very good. Okay, so I feel like these ones are pretty straightforward. You just have to remember that that Roman numeral is telling you the charge on that metal. Okay, then you just solve it just like any of the other ionic compounds. But now if you're working on this, I know that Cr is what? Chromium, so I'm going to put his name. Leave some space. And I know that S is sulfide. So remember, first part of the nonmetal plus the IDE. So I know this is chromium sulfide. But if you see iron, copper, chromium, you know you've got to add that Roman numeral. So I've got to figure out what the charge is on the chromium. So if I have Cr2S3, what do you know the charge on the sulfur is? Right? You see that it is in group 6, so 8 minus 6 tells you it's a -2. So do you see that the -2 and the 2 on the chromium are the same? Well, then that tells you the charge on the chromium is the same as the number for the sulfur, so that is a +3. So think of it as almost like a reverse swap. As long as the charge on the metal is equal to the charge on, or sorry, the number for the metal is equal to the charge on the non-metal, you're basically doing a reverse swap to figure out the charge. So what goes between the chromium and the sulfide? Yep, the Roman numeral 3. Okay, so then the last one, Fe is what? Iron. So this is iron, and then F, fluoride. Fluoride. So then do the exact same thing what we just had to do with that chromium sulfide. So you've got Fe, and you've got Cl3. I know the charge on chlorine is -1, and I know in the formula, FeCl3 means I have 1 iron. Remember, you don't write it if there's only 1, but you see that those are the same. So then that tells me that the charge on the iron is +3. Okay, just doing like a reverse swap to be able to figure it out. So now the Roman numeral I put between the words iron and fluoride would be 1, 2, 3. Those are the only three that you're going to see. So looking back, you can see that there are the ones that I marked off. There's quite a few transition metals. You can't tell the charge on the transition metal automatically. Like just from looking at where chromium is, you really can't tell that it should be a +2 or a +3. And it all has to do with that orbital that it's got. This one has like a bigger orbital, and so they can kind of stabilize themselves by losing kind of an odd or weird number of electrons. And these ones have the chance or potential of losing more than one and still being stable. Okay, so those are the steps for those. Now, there's one other oddball in the list. Okay, so we have just regular generic ionic compounds. Then we have those three transition metals. But the other ones that we're going to come upon and you're going to see regularly are what are called polyatomic ions. Poly means what? Yeah, poly means many. So polyatomic means many atoms, just from its name. So these are ionic compounds where you have multiple nonmetals that together have a charge. So one example of this is NO3. So they call this, it's a nitrogen with 3 oxygens. The only way that this can form a group is if it actually has an extra electron. That creates their stable grouping or octet. And it has to, so the whole thing has a negative charge. So they don't call it nitrogen oxide or anything like that. The group collectively has a name. It is the nitrate ion. And anytime you see this in a molecule, you don't split the nitrogen and oxygen up in naming. It's just called the nitrate ion. So for example, where potassium and the nitrate ion combine, down in this bottom example, same thing that you did with ionic compounds, you just assign the charges, swap the charges to figure out the simplest ratio for their formula. So you know that potassium is a what? What's its charge? It's a +1. And if you know the nitrate, recognizing the nitrate, it'll always have a -1 charge. So see that they're like 1 and 1, like sodium and chlorine. So they're 1 and 1, so they just exist as KNO3. So in their name, you still use the whole name of the metal, but instead of like splitting this up, you just keep the name of the polyatomic. So this is potassium. What? Nitrate. So make sure that this, so you remember this is different than potassium nitride. Potassium nitride would just be potassium and a nitrogen combining. But potassium nitrate tells you that it's that polyatomic. So there are 7 of these, okay? And just to show you, you don't have to memorize all of these. There are 7 that are the common ones. I've got them in boxes, so that's the ones on your slides, the PowerPoints, if you printed them out. It's the ones that are in boxes, and there are 7 of them. So if you look, you can see that there are 5 here, and then there's 2 on the other page. Notice that there's a lot of them, though. Like, for example, carbon. Carbon can make multiple different types of polyatomic ions by combining with oxygen in different ways, by even combining with nitrogen. The nitrogen can form 3 different types. There's a nitrate, a nitrite. So there's lots of different names to those polyatomics, but the ones that are really the most common are the ones that I've got in a box. Here's the other table, because I couldn't fit it all on one page. But look, like sulfur can actually form 4 different combinations. Phosphorus can form 4. Well, you don't really need to, because we're only picking 1 out of each. So if you have some, what I will tell you, so sulfate, or the 8, means that it always has the maximum number of oxygens. And then one less is the ite. So they do go through, like if you look like phosphate to phosphite, they still end up having the same charge. They just have one less oxygen. But these are the ones that you need to worry about, these. Okay? So we have the hydroxide, which is OH. And I will tell you, hydroxide is the characteristic polyatomic ion for things that are bases. So things like lye, Drano, oven cleaner, even baking soda, that hydroxide ion is the characteristic base ion. Then we have the only positive polyatomic ion is the ammonium ion. So that one's an NH4, but actually has a +1. Hydroxide is an OH and always has a negative charge. The nitrate is another nitrogen. Nitrates are commonly used in fertilizers because plants need nitrogen in order to grow. So people spray nitrogen fertilizers on soil, crops, grass in order to get them to grow. And that's NO3 with a -1 charge. The charge is always the same for these polyatomics. So it's not going to be sometimes this one, sometimes that one. And so this is probably ones that you want to make sure that you put on your note card, their names and their formulas, so that you can find them and compare them. The chlorates are commonly found in disinfectants. Bleach is sodium hypochlorite, so it's a form similar to it.
What are the things after it?
What do you mean after it?
Like the NaOH and the NH4, Cl.
Oh, these are examples.
Oh, so
The stuff written in purple are the examples. The ones that I've got that are listed, typed, that are boxed, those are the polyatomic
that's
ions.
what you're talking about right now. Okay.
Yep. So hydroxide, ammonium, nitrate, chlorate, carbonate, which is like what you find in baking soda or baking powder. Sodium carbonate is CO3 and has a -2 charge. So remember, in this formula, this means I have 1 carbon and 3 oxygens, but the charge is a -2 or 2 negative. Either one's fine. Okay? So when you look at these, it's like CO3, 1 carbon, 3 oxygens. Then when you see 2- or -2, that's telling you the charge. Sulfate is an SO4, 1 sulfur, 4 oxygens, and collectively they have 2 extra electrons, and so that's why it's got a -2 charge. And the phosphate has the highest charge of all of the polyatomics. It has 4 oxygens, 1 phosphorus, 4 oxygens with a -3 charge. So if you're given the name, like sodium hydroxide, and you want to write the formula, you do it just like anything else. The key thing is you have to remember what the formula of the polyatomic is. So if you see NaOH, well, you're still using the full name of the metal, so this would still be what? Na is sodium, right? So it would still be sodium, but now OH, you have to recognize that that is not an oxygen, hydrogen naming type of thing. The OH is the hydroxide. So you don't use ID at the end. You don't have to worry about that part. You just use the whole name of the polyatomic. No shortening of it or anything like that. So what about this one? So if you see NH4, it's the so this would be ammonium. And now if the Cl's at the end, it is chloride, just like all other Cl's are. So when you have the formula and there's a polyatomic, just give the name of the polyatomic. You don't have to worry about how to name the grouping. So what about this one? Yep, so it's magnesium nitrate. Do you remember when you were doing balancing equations? Do you remember seeing things in parentheses with numbers on the outside? right? That you had to go in, like when you were balancing, all of those were polyatomic ions. If you go back and look at your balancing equation sheets, you will see that everything that you've got that's in those parentheses were things like CO3, SO4, PO4. They were all these polyatomics. So when I go to write their formula, if you have more than one polyatomic, you don't break it up. It stays together. You put a parentheses around it, and then you can do your swapping of the charges to figure out the formula. So like with Mg and NO3, the reason that ends up with this parentheses, what's the charge on magnesium? It's a +2 because it's in group 2, right? So it's a +2. Now the nitrate, I know the charge on the nitrate. The only way that I know that is because I've memorized it, or you got to have your note card with those written down. So you would know the charge on the nitrate's a -1. So see in this, swapping the charges, that tells me I have 1 magnesium because the charge on the nitrate's a -1. I'm going to have 2 magnesiums, but I have +2 for magnesium, so I have 2 nitrates. This is why I have to have the parentheses around the entire polyatomic to show there's 2 of them. So let's do this one then. So potassium chlorate. What is potassium? We're going to write the formula now. Potassium is K, and its charge is a +1. And then the chlorate is ClO3 with the negative, right? That's the chlorate here. So you're just going to write the entire polyatomic with its charge. So this one, pretty simple. Do you see that it's a 1 and 1? Potassium has a +1, the chlorate's a -1. So they're just going to exist as KClO3. I don't have to use parentheses because there's only 1 of each. So just like sodium chloride, you don't have to have more than 1 if they're balanced in their charge. But now what about lithium carbonate? What's the charge on lithium? So lithium's a +1, it's in group 1. Now the carbonate is, CO3 with a -2, or 2-. So now see, they're not the same. So the charges are not the same, so now you're going to swap. So what becomes the number of lithium? So I end up with Li2, and carbonate is just 1, so it's CO3. I don't need parentheses around the carbonate because in this one, the carbonate is found singly. So what about, do this one. What about aluminum sulfate? So you tell me, what's aluminum? The formula? Al. And its charge? It's a plus what? +3. Find aluminum on the periodic table. See at the top, it's 3A. It's really the only metal you have to worry about with a +3 charge. So the sulfate is what? The formula, SO4, and its charge is a -2. So these are not the same. So now I've got to do the swap. So how many aluminum do I end up with? So I'll have Al2. The charge on the sulfate tells me how many aluminum. What's going to be the number of sulfates? 3. And so in this one, SO4, I'm going to end up with 3, but I have to put the parentheses for this one. Okay? So if there's more than one polyatomic, when you reach the formula, use parentheses to keep them kind of grouped together so you don't split them up. Okay? Ammonium phosphate. So what's ammonium? So it's NH4 with the plus, and then phosphate is PO4 with a -3. So notice they're not the same, so I got to swap them. So what do I got to do to the NH4? NH4 will need the parentheses because what goes on the outside? The 3. And then the PO4, do I have to use parentheses for it? No, because see how the +1 of ammonium, that means that I'm only going to have one phosphate. So PO4 would just be a 1. So you only have to use parentheses if there's more than one polyatomic. Okay, so I want you to practice these. So we're going down. The first 4 is going from the name to the formula. The last 4 are going from the formula to the name.
So anytime they don't match, is that when you put parentheses?
So anytime they don't match, you're going to have to swap. And if the polyatomic is anything other than 1, you have to have parentheses. If the polyatomic is just a 1, you don't need them. But if it's anything other than 1, then you do. Okay? Yeah, so the first 4 are really, I think, the more challenging. The last 4 are pretty straightforward. You just got to make sure that you remember the name for the polyatomic. So I would start off, just add this to your list. These 7, it's just these 7. You're not going to see any others. It'll just be these 7. Their names and what their formula is with their charge, because you want to make sure that you remember the charge so that you can figure out what formulas they would have. All right, so first one. So sodium nitrate, what did you end up with? First you put symbols in their charges. So sodium is Na with a +1, and you can write +1 or just a plus, either one's fine. But then when you see nitrate, you want to add NO3 with a negative. So notice when you look at them, see they're 1 and 1, so they're fine just the way they're written. So it's just NaNO3. No parentheses needed because it's a +1 and a -1. How about calcium phosphate? Calcium is a Ca with a +2. Phosphate is PO4 with a -3. So this one, they're not the same. So when you do the swap, the number on calcium tells you how many phosphates. The charge on the phosphates tells you how many calcium. So it would be Ca3, and then parentheses, PO4, 2. Okay, so if it ends up the polyatomic has a 1, you don't need the parentheses. But if it's anything else, put the parentheses and just put that number outside of it. Lithium sulfate. Lithium is Li, and it is a +1. Sulfate is SO4 with a -2, or 2 negative, either one. So they're not the same, so I'm going to swap them. Number on the lithium tells me how many sulfate. Charge on the sulfate tells me how many lithium. So the formula is Li2SO4. Since this SO4, there's only 1, you don't need to have any parentheses to it. That looks like Liz. Sorry, put a 2 down lower. All right, magnesium chlorate. So magnesium is with a +2. Right? It's in group 2, so it's a +2. The chlorate, though, Cl, it's Cl. So remember, chlorine is Cl, and then O3 with a negative charge. Since they're not the same, I've got to swap them. So how many magnesium? Just 1 magnesium and parentheses 2. Okay? Not terrible. Just a matter of doing it exactly the same. If you've got the name, you got to assign the charges, swap them, simplify if possible. So K2SO4, what's that one called? Potassium, whole name of the metal, sulfate, just the name of the polyatomic. So you don't have to split up the sulfur oxygen, naming them separate. The SO4 is a sulfate. So NH4Br, ammonium, right? So NH4, that one's the only kind of oddball, like to put a little note. This is still an ionic compound. Even though when you look at this, do you see nitrogen, hydrogen, bromine? Nitrogen and bromine are over in the nonmetals. Remember, hydrogen acts like the nonmetal. So when you look at it, you're like, wait, there's no metal. But you have to remember that NH4 is a positive charge, so it's still an ionic compound. Because the NH4 has a positive charge, that's an ionic compound. Then it's NH4 is always just called the ammonium, so then the bromine makes bromide. Okay, BeOH2. Beryllium hydroxide. And then Al2CO33. Aluminum carbonate. Okay, so just go through and practice these ones. Practice sort of like doing their combinations, looking at the formula of the metal and the polyatomic, swapping them to make sure that you can figure out the formula, and then just go back, practice their names. There's a couple of good examples that in your book as well.
So I thought with the polyatomic ions, when they did have a charge on them, they would have a Roman numeral.
Nope. Not polyatomics, only transition. The transit, because polyatomics can only have one charge, right? So the nitrate ion is always NO3 with a -1. It's never going to have a different charge, because remember that the nitrogens and oxygens, the only way they can exist is by adding an extra electron. That kind of like fulfills their octets in their like big globule size.
So when the transitional metals have a charge, that's when the Roman numeral comes into play.
Correct. So for you, just remember it's iron, copper, and chromium. Okay? It's only those three that you've got to remember. Those metals are always going to have a Roman numeral because of the potential for different charges they can have.
So we should add what we just did over note card, you said? 'Cause those are the
I would add that. See the ones in the 7? You don't have to remember any but these 7. And the only reason is a lot of solutions, like magnesium sulfate. You may end up giving solutions to patients. You may end up with some buffer solutions, with medications, IV solutions that have this to them. Okay, so recognizing those polyatomic ions is going to make you make less mistakes when trying to like pick out correct solutions by recognizing that sulfate. Oh, that's that SO4 that I'm looking for, so that you're not like looking for something with just sulfur. Okay, so recognizing the polyatomics exist always in these like discrete types. All right, so just importance of ionic compounds. Ionic compounds like table salt, sodium chloride. Okay, so it's a really stable ion. Sodium chloride, though, when you mix it into water, it does not stay as sodium chloride. When you drop salt crystals in water and stir it up, you see that it completely disappears, it dissolves. And when it does this, they form sodium ions and chloride ions. And they will use, this started off as a solid and a liquid, so they will use that term aqueous. So aqueous tells you that it's dissolved in water, it's in a liquid solution. So when you eat the salty French fries, as soon as that sodium chloride hits your tongue, it hits the saliva and it begins to dissolve. That is detected as a salty. Sodium ions trigger the salty receptors on your tongue, so you notice the salt flavor. When you swallow this, it gets absorbed really quick. These don't ever have to get digested. Salts dissolve. There's no digestion that occurs. They get absorbed rapidly into the bloodstream. So in the bloodstream, they don't float around like NaCl. They float around independently. So the sodium ions and the chloride ions are not connected. So I don't really think of sodium as ionic compounds as being very strong, right? These don't tend to stay together. Instead, since they separate, they act more independently. So sodium as an ion is a major electrolyte or ion that is found in the blood. So this is found in the blood, and it's really a major water balancer. So it helps in regulating the amount of fluid that is retained in the blood. And anybody that's had a really high salt meal, you've probably experienced mild edema. So edema is when you have fluid that begins to collect in the spaces under the skin. So you might notice, like if you go out and you have like the fried chicken with French fries, or the mashed potatoes with gravy and the sodium with the friedness, okay? So there's a lot of salt in the preparation of most of those foods. And so that means that you're ingesting higher levels than normal. So that sodium, if it stayed in your blood, it would cause more water to collect and be held in the blood. What would that do to your blood pressure? Make it go up. Because if there's a lot of sodium, that means there's a lot of water. And think about your blood vessels as tubes that can stretch. So if there's a lot of water and salt in the blood, that means those tubes are going to get stretched and the blood pressure is going to go up. So typically, this fluid gets pushed out of the blood and into areas that they call the tissues, like the interstitial spaces, areas underneath the skin. And so how do your rings feel? They get tight. Okay, you may even end up with the puffy ankle thing going on, okay, because the fluid that begins to collect in the lower extremities, typically it's under the skin and creates this slight edema. Now, as long as you have normal kidney functioning, as long as you have normal blood pressure, normal heart contractility and circulation, does this last forever? No. Okay, this usually is a phenomenon that you might notice for 6 to 12 hours. Your kidneys will just get rid of this excess. But patients that have heart conditions, patients whose heart is not circulating blood as easily, they may begin to notice that they have chronic edema. They have this chronic swelling because the blood is having a hard time circulating, getting back to the kidneys, and filtering out appropriately. So what does the doctor tell them? If you want to lower your blood pressure, what do you do in your diet? Try to eat less salt, because less salt will decrease the amount of fluid that is being retained and help to decrease that amount of blood pressure. So that's just one of the things that sodium's responsible for. Calcium. So people always think of calcium. What do you automatically think of? Milk and bones, right? So calcium's really interesting in that calcium is involved in a lot of steps. Calcium's involved in transferring nerve stimuli from one neuron to another. Calcium is really important in blood clotting. You don't have enough calcium, you're not going to clot very well. Calcium's important in muscle contraction. So there's lots of cells that use calcium, but most of the calcium you ingest goes where? To your bones. So the bones are literally like a calcium bank. That is where it's stored so that it can be sent when needed to specific cells. But the benefit is, in the bones, what does it add? Strength, because your bones are your weight-bearing structures. So that calcium is almost like cement being added to the bone to help it be able to resist stress and bending. People that don't get enough calcium in their diet, especially women, and the reason for this is menopause, estrogen actually improves your absorption of calcium. So when you hit menopause, which is somewhere around 50, estrogen levels begin to decrease. So right along with that, what happens to calcium absorption? It's going to go down as well. And so if you begin to decrease in calcium absorption, but your nerves, muscles, blood clotting need calcium, then your body is going to get calcium from where? If it's not getting absorbed, it's going to get pulled out of your bones. And that can lead to what? Osteoporosis. That can lead to brittle bones. So that is the reason why they say to try and increase the amount of calcium that you ingest prior to menopause, because you are going to start losing it from age 50 onward. So the 20s, 30s, and 40s are really times to try and maximize the amount of calcium storage in bones so that you don't end up with osteoporosis. Yeah, so if you have like a complete hysterectomy, that means that they remove the ovaries. So you can make some estrogen from fat, but most of your estrogen comes from the ovaries, which make your eggs. And so that's where they say you can take like vitamin D helps with calcium absorption. Doing more weight-bearing exercise can help with promoting bone and calcium, like kind of like storage. So those can help, but that's always the challenge. And that's why there's, it's usually in your 20s, 30s, and 40s, you don't think about it, right? That's not when you're like thinking, oh, I better like make sure that I'm doing weight-bearing exercise and eat an extra piece of cheese to try and get some calcium storage going. And a lot of people that are like lactose intolerant, they avoid anything with calcium, but that's a challenge, okay? Because you can be setting yourself up for brittle bones, and brittle bones are like when people have their hip breaks and then they fall. So they didn't fall and break a hip. It's because the neck of the femur got so weak, it actually fractured just from weight bearing, okay? And that takes away your individual living, quality of life, all of that then ends up being an issue. So here's another one. So in looking at this is iron with a +2 charge, so this would be an iron 2 ionic compound, okay, compared to the iron 3. This is typically how it is brought in. Any kind of red meat is going to have iron in this form. Spinach, like Popeye, right? So green leafy vegetables also have some iron in them. Raisins have iron in them. So this is one that's really specific because iron is used to make what? It's used to make red blood cells. Iron is the reason that your blood is red, is because of the red iron 2 ion. Without this, so if like you're a vegetarian, okay, and you're not a big salad eater, well, you're in a lot of trouble if you're a vegetarian. You don't eat a lot of salads because like, I don't know what you're going to eat. But if you don't, what can end up happening? Not enough red blood cells leads to anemia, okay? So making sure that you're getting the right amount, a balanced amount of electrolytes. You don't want too much, you don't want too little. Making sure that you're getting a balanced amount in the diet is important. I always think of ionic compounds as being more functional, right? So they're helping with water balance, they're helping with blood clotting, they're helping with bone strength. So they're not so much building big structures. They don't build the bone, they just make the bone hard, okay? So they don't help in making the red blood cell, they just let red blood cells carry oxygen. So you can have red blood cells, but they don't carry oxygen very well if they don't have enough iron. So you'll see these like kind of over and over and over. And remembering back, notice that none of these except for, none of these are CHM. None of these are carbon, hydrogen, oxygen, and nitrogen. Instead, sodium, potassium, calcium, magnesium, chlorine, those are all what? Which group do they fall into? They're not the main group. They are considered the minor, right? So they're the group of 7. The only other ones, the phosphorus and sulfur, those all are comprised in those 7 minor elements. So they're important. They make up that like 3.9% of the atoms that are found in the body, but they're much more functional in nature, helping the body function the way that it needs to. So that moves into covalent molecules. So if you have a hydrogen atom, right? So remember, hydrogen has just 1 valence electron. It's over in group 1. And all it needs is 1 more to make it like helium, because helium's the noble gas. So if I have 2 hydrogens, both of them need 1 more electron, but neither of them can pull an electron from the other because they're exactly the same. So this is different than like sodium and chlorine. Sodium only has 1, chlorine has 7. So that's a pretty easy transfer. But here, the hydrogen's not going to give up its electron to another hydrogen. The only way these two can exist stably is if they share. So this sharing that occurs means that these 2 atoms have to get close together so that their electrons remember electrons are constantly moving, so their electrons actually come into the same orbital region. So you just put the 2 atoms close together. The 2 dots in between, one is the purple hydrogen's electron, the other one is the blue hydrogen's electron. And now this hydrogen can behave as if it has two, which makes it like helium. This hydrogen can also behave as if it's like two. So I always think of like covalent bonds. This is sort of like shared custody, right? So if we're equally sharing custody, then that means half and half. So these electrons are always moving. They're not like stuck right in between. They go back and forth, okay? But half of the time they're with the blue hydrogen, half the time they're with the purple hydrogen. So they're just going back and forth. So it is as if both of those hydrogens have 2 electrons each, which make it stable like helium. Hydrogen's an oddball. Hydrogen only needs 1 bond. It has 1 electron, only needs 1 bond in order to be stable. So that they call a covalent bond. This sharing versus a transfer, there's no ions that are formed here. This is a single covalent bond. And this is all hydrogen will ever do. Hydrogen will only ever form a single bond. So you might have seen it like this. So you've probably seen molecules drawn with dashes. A dash represents 1 pair of electrons, and it's linking the 2 atoms that are sharing those electrons. In fact, this is how you find hydrogen gas. Hydrogen gas in nature is always found as H2. 2 hydrogens, they call it a diatomic element. So you don't ever find hydrogen atoms. They're too reactive, but they'll form this hydrogen H2 molecule and be more stable. So there's another characteristics. We're always talking about nonmetals, and we're going to include hydrogen in our list. Hydrogen and nonmetals. So when you're looking at the periodic table, remember the nonmetals are the ones that are to the right of the zigzag line. So here we are talking about carbon, nitrogen, oxygen, fluorine. Then we're talking about phosphorus, sulfur, chlorine, bromine, and iodine. Those are those nonmetals. Remember the other ones along the zigzag line are those metalloids. So these are really just them. One of these also only makes a single bond. Which one do you think it is? Is it the column of carbon, nitrogen, oxygen, or fluorine? Needs to have 8. It's the column with fluorine, right? So if you look at fluorine and you draw its Lewis dot, remember that fluorine, chlorine, bromine, and iodine, when they form ionic compounds, they always gain 1 electron. Well, if they're combining with other nonmetals, then they're going to share 1 electron and 1 electron only. So fluorine can form a single covalent bond. It can do it right here. But you notice all the other electrons now are full, and it would have 8. So fluorine, chlorine, bromine, and iodine will only ever have a single covalent bond, like hydrogen. So really, it's just these ones that are the challenge. The carbon, nitrogen, oxygen, phosphorus, and sulfur. Those are the ones that end up doing the potential of more than just a single bond, because they have to share more electrons to form the octet. So here's the example with chlorine. So if I have 2 chlorines side by side, do you see that each chlorine can't pull an electron because they're exactly the same? But if they shift closer together, those electrons that don't have a pair can now be shared between. So remember, that means, though, that those little red electrons spend 50% of the time with the left chlorine, 50% of the time with the right chlorine. So they're going back and forth, back and forth. Now, these electrons that are up here, see how I have 1, 2, 3, 4, 5, 6? That chlorine has 6 electrons that are not in between the 2 chlorines. Those 6 electrons, they sometimes call them lone pairs or non-bonding electrons. So non-bonding electron pairs, also sometimes called lone electrons. I like non-bonding because it tells you exactly what they are. So these are electrons that belong to the chlorine. They do not go over and hang out with the other chlorine once in a while. They are basically only in the orbital around the chlorine that they're attached to. so they don't get shared with others. That is where the term non-bonding comes from. They don't form covalent bonds with other molecules. They exist to make chlorine's octet stable. So chlorine has 6 non-bonding electrons, or 3 pairs, and only 1 bonding pair to create their 8. Okay, so we've got this one. Pretty simple. H, you're only ever going to see it with 1 line, right? Hydrogen's only ever going to form a single covalent bond. Same thing with fluorine. Fluorine, you can put all the dots you want, 6 dots, but at 2 will only ever form a single bond. But now what about carbon? Okay, so do you see that carbon has 4 valence electrons? Remember, it's in group 4. So it needs 8. So the only way for carbon to form a stable octet is that it's going to have to share its electrons with 4 other things. Okay, it's going to have to make 4 bonds in order to be stable. What about nitrogen? Nitrogen's going to end up needing 3 in order to create the stability. And so if you look, you can see there's going to have to be 1 here, 1 here, 1 here. There's going to have to be 3 electrons that are going to get shared with some other atom or atoms in order to be stable. Now what about oxygen? Yep, so oxygen's just going to be 2. So oxygen's going to have a covalent bond to other electrons, 2 other atoms to create stability. Now, if these are all single bonds, then that means carbon's always going to have 4 single bonds. Nitrogen would always have 3 single bonds. Oxygen would always have 2. But there is the potential of what they call a double bond or even a triple bond. Triple bonds are not that common, but possible. So in this one, see where carbon can form the 4 single bonds. But if you have certain atoms combining, they may have to share more than 1 pair of electrons. And so under those circumstances, you may end up with a double bond and 2 single bonds. Do you see that still 4? So everybody see that still equals 4, and carbon has to have 4 bonds. It could be a double and 2 singles. It could even be 2 double bonds. As long as carbon has 4 pairs of electrons that are being shared, it will be stable. Very rarely, carbon will form a triple bond and a single bond in order to create that stable octet, but it could happen. It's always like the last ditch thing that you do, okay? Always try to just make single bonds first. You only do multiple bonds if there's no other option. So here shows sort of some of the different ways. Remember I said that with hydrogen, with fluorine, chlorine, bromine, and iodine, 1 bond, that's it, okay? They're never going to have more than 1. And that makes them kind of like the things that you always add around the outside. You almost never have them as like the center atom. You don't end up starting with these. You're going to start to build molecules using either carbon, nitrogen, or oxygen. So remember, these are all the CHM. So these are the ones that are very common. Okay? So the formula tells us how many atoms in the molecule. And no, we're not going to draw glucose yet. That'll be chapter 6. But so if you see C6H12O6, you know that means 6 carbons, 12 hydrogens, 6 oxygens. So the formula, you have to use all of the atoms. So if I'm going to draw CH4. So with CH4, I know I have to use 1 carbon and 4 hydrogens. So with covalent, unlike ionic, with covalent, I will always give you the formula. So you're never guessing. You're never like, well, how many of each? And you don't have to do charges or swapping or any of that. Instead, you're given the formula. So with these, the first thing that you do is you want to make a list. You want to make a list of the atoms in your molecule so that you know how many electrons do I have to use and how many bonds does each have. So remember, except for hydrogen, everything ends up having to be electrons and bonds always have to equal 8. So the octet rule comes into play with this. Hydrogen, though, is the exception because hydrogen only ever needs 1 more, so a total of 2, right? Because remember, 2 is like helium. So that, if hydrogen just has 2 electrons, it's like helium, which is a noble gas. So remember that that's the one that's like never follows the octet, and it's because that first energy level can only hold 2 electrons. So hydrogen and helium have that exception, right? So if I list CH4, 1 carbon, 4 hydrogens. If I look at carbon, periodic table, group 4A tells me it has 4 electrons. It has 4 electrons, which means I know it's going to have to form 4 bonds somehow in order to have 8. It's going to share its electrons with electrons of other atoms in order to have the total of 8. Well, each hydrogen has 1 electron, and I know each hydrogen only needs 1 bond. So the next rule is that you always start with the atom that needs the most bonds. And I always put that on the paper first. I kind of make it my center or my central atom. Okay, so in this one, I would always put down the carbon first. Carbon with its valence electrons. And remember that the rule is always to spread them out. Okay, carbon, just spread them out. You may have to move them, but start with them spread out, one on either side, above, below, left, and right. So there's the 4 electrons. So now I've got 4 hydrogens left to add. So can you see that you would just put and form a single covalent bond between the green carbon electron and we'll use the purple hydrogen. So that's a single covalent bond. This is a single covalent bond. Here, single covalent bond, and then at the bottom. So you see that I'm only forming 1 pair shared between carbon and each of those hydrogens, but now the hydrogens have their 2, 2, 2, and 2, right? So they each have 2, which is all they'll ever have. But if I look at carbon now has 8. 2 above, 2 below, 2 to the left, 2 to the right. So I can take and simplify this, getting rid of the dots, just using a dash to represent each pair of electrons that's shared. They call it a Lewis structure. So Lewis structure uses lines instead of all the electrons. Notice there's no non-bonding electrons. Hydrogen does not have any non-bonding electrons. Carbon does not have any non-bonding electrons. All of carbon's electrons are involved in covalent bonds, and so is hydrogen's. Because remember, hydrogen's only ever going to have a single bond. Okay, so let's practice some. So we just did this one. So let's do water, H2O. So in each one, what you're always going to do is figure out which one needs the most bonds. That one's always the one you start with. So what do you know about hydrogen? Hydrogen has 1 electron and needs 1 bond. 1 electron and needs 1 bond, always. So I know I'm not going to start with hydrogen. Oxygen, though, has, it's in group 6 electrons, which that's how I know it needs 2 bonds, because it's got to have 8. The electrons plus bonds will always equal 8, except for hydrogen. Hydrogen's only going to be 2. So that tells me to start with oxygen. Start with the atom that needs the most bonds. So I start with oxygen. When I put it down, it doesn't matter where you put your dots, just so long as 2 sides end up with 2 dots and 2 sides end up with 1 dot, like this, okay? So it would not be wrong if you put your dots like this. That's not wrong, okay? I don't care. It would not be wrong if you put your dots like this. That's fine too. The rule is, with oxygen, 2 sides need 2 dots, 2 sides need 1 dot. Doesn't matter where they go. And in fact, if you remember in lab last week, like we were like flipping them around. Once we build molecules, you can like flip this around so that you would make it match what mine would look like. So don't feel like super stressed about where your dots are. Just remember, you don't want more than 2 on a side when just doing doing like the Lewis dot structure for a single atom. No more than 2 on a side, and spread them out, okay? So don't put like 4 on one side and 2 on the other side. Spread them out, 2 dots on 2 sides, single dots on 2 sides with oxygen. So now I'm just going to add the hydrogen. So can you see it? Basically, there's 2 single electrons, and then I have 2 hydrogens. So I'm just going to form a single bond between the hydrogen and the oxygen. Right? So I could put it up here. You might have drawn it like this. That's completely fine. Right? Even this one up here, single, single, still completely fine. Now, if you count, you can see all 8. Right? So if you kind of like go around, can you see that the oxygen has its 8? So it has the octet, and each hydrogen has 2. I'd see the same thing with any of them. None of those are wrong. They're all fine. Okay? The key thing is you want to make sure that you have a single pair between the oxygen and the hydrogen, another single pair between the other hydrogen with the oxygen. And then the areas that don't have pairs should have 2 dots on either side. So if I'm going to convert this to a Lewis structure, so this would be that. All I'm doing is taking the shared pair out and changing it to a line. But I keep, notice in this, oxygen does have non-bonding pairs, so I keep them. So these are those non-bonding pairs. These are the electrons that belong to oxygen. They don't go hang out with hydrogen at all. They just hang out right around oxygen. They belong to oxygen exclusively. And oxygen has 2 of them, 2 pairs of non-bonding electrons. They come into play with shape because we're going to talk about them. All right. We'll pick up here next time. So NH3 and CH2O, CO2. These are really the 5 basic shapes that we're going to talk about. We are really not going to do like really, really large shapes. We're going to stick with like 3, 4, 5, maybe 6 atoms per molecule as a maximum in terms of drawing these. So practice these ones because these are really going to be like really good examples that you'll see on an exam. Okay? If you're feeling like super adventurous, you can do the HCN.